Dark openings are one of the most bewildering and particular peculiarities in the universe, remaining a subject of phenomenal survey and interest among space specialists and physicists alike. These divine items, characterized by their colossal gravitational pull and the absolute shortfall of light emanation, address a cutoff past which the known laws of actual science no longer apply. First theorized by Albert Einstein in 1916 as an outcome of his hypothesis of general relativity, dark openings were just hypothetical until mechanical headways allowed for their circuitous identification during the 20th century. The defining moment came during the 1960s when space experts, contemplating the Cygnus gathering of stars, coincidentally found a surprising heavenly item, a splendid blue star radiating high-energy X-rays. This star, circling an imperceptible body, opposed customary clarifications until it was uncovered to be in a gravitational relationship with a monstrous dark opening, Cygnus X1. The disclosure of Cygnus X1 gave obvious proof for the presence of dark openings and denoted the start of a new era of examination into these grandiose puzzlers. Cygnus X1, situated around 6,000 light-years from Earth, has stunning properties. It is extraordinarily thick and applies a gravitational force so severe that not even light can escape its grip. This defining highlight earned it the name dark opening, typifying the substance of these baffling objects. Subsequent research has uncovered an assortment of dark openings dispersed throughout the universe, with estimates suggesting that the Milky Way alone may hold more than 100 million dark openings. In spite of their slippery nature, which makes direct discovery testing difficult, space experts have identified a few candidates within our galaxy, ranging from heavenly mass dark openings formed from the remains of monstrous stars to very large dark openings located at the centers of galaxies. The gravitational impact of dark openings extends far beyond their nearby area, shaping the development of vast structures and impacting the destiny of surrounding matter. Objects that venture too close to a dark opening face a fate determined by its constant power. They are drawn inevitably toward the event horizon, the last boundary, where they are exposed to extreme tidal forces and, eventually, consumed by the peculiarity at the dark opening center. This horrendous interaction, known as spaghettification, is the ultimate indication of a dark opening's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes so intense that it is stretched and twisted into a filamentary shape, resembling strands of spaghetti. The forces applied by the dark opening overwhelm the internal bonds keeping the object intact, causing it to disintegrate into a surge of matter that eventually converges with the peculiarity. In spite of the charm of dark openings as laboratories for testing the limits of physical theory, they remain shrouded in mystery. The quest to unravel their secrets continues, driven by a desire to understand the fundamental nature of space-time and gravity itself. In the vastness of the universe, dark openings stand as silent sentinels, calling humanity to explore the depths of the unknown and extend the limits of human knowledge. In spite of the enormous distance separating us from the closest dark opening, around 1,500 light-years away, various kinds of feedback about their potential impact persist. In 2021, scientists achieved a groundbreaking leap by capturing the first clear picture of a dark opening, specifically M87, situated at the center of the M87 galaxy. This wonderful accomplishment provided significant insights into the nature of dark openings and their tricky structure. The visual data revealed that dark openings have complex layers, challenging the conventional wisdom of them as singular entities of pure nothingness. Through careful investigation, researchers identified 3 distinct layers within a dark opening. At the peripheral layer lies the event horizon, a critical limit marking the final turning point. Once an object passes this boundary, gravitational forces become insurmountable, ensuring its inevitable fall into the dark opening's depths. Moving inward, the photon sphere is the second layer, where light circles the dark opening in eternal bondage. Any photons that venture into this domain surrender to the overwhelming gravitational pull, trapped forever inside the dark opening's vast embrace. At the core of the dark opening lies the peculiarity, the third and final layer, where the laws of physics break down and the natural laws governing the universe cease to apply. This plunges specialists into a domain of profound uncertainty and theoretical hypothesis. The complexity of dark openings and their inherent variability present significant challenges to our understanding. While they share a common 3-layer structure, each dark opening exhibits unique properties and behaviors, defying basic categorization. As a result, traditional methods of scientific inquiry prove inadequate for studying these infinite behemoths, requiring innovative approaches to unravel their mysteries. Indirect observation remains the primary method for studying dark openings, as direct examination is rendered impractical by the enormous barriers posed by their gravitational forces. Efforts to launch probes into dark openings would inevitably result in their destruction, crushed into oblivion by the relentless forces at play. Nevertheless, scientists continue in their mission to uncover the secrets of these astronomical monsters. Various theories, ranging from stellar collapse to astronomical phenomena, offer intriguing glimpses into their origins and behavior. Notably, NASA's investigation of the astronomical center of M87 uncovered undeniable evidence of a supermassive dark opening exerting its gravitational influence over vast cosmic scales. Despite these challenges, the quest for knowledge persists unabated, driven by humanity's innate curiosity and hunger for understanding. While the conundrum of dark openings may escape immediate comprehension, the enduring commitment to scientific inquiry promises to illuminate the darkest corners of the universe, unraveling the profound secrets concealed within. Roy Kerr's groundbreaking work in 1963 introduced a paradigm-shifting perspective on dark openings, proposing a revolutionary theory of rotating dark openings that challenged traditional understandings. Key to Kerr's model was the concept of the ergosphere, a region surrounding the dark opening where disparate forces balance gravitational collapse, preventing matter from falling further inward. This novel region exhibited curious deviations from conventional material science, alluding to the significant secrets covered inside dark openings. Anyway, the most fascinating ramifications of Reveille hypothesis were the forecast of an Einstein-Rosen bridge, casually known as a wormhole. This theoretical design addresses a likely passage through spacetime, offering a channel between far-off districts of the universe or even parallel universes. The possibility of wormholes stems from the many-sided transaction between reality as portrayed by Einstein's hypothesis of general relativity. In this structure, presence is woven together, framing a four-layered texture known as spacetime. Huge articles twist this texture, making gravitational fields that impact the movement of encompassing matter. Wormholes basically go about as easy routes through this astronomical texture, associating far-off focuses in spacetime and possibly empowering quick crossing across enormous distances. Anyway, the strength and reasonableness of wormholes remain subjects of extreme theory and banter among hypothetical physicists. While the presence of wormholes offers enticing opportunities for interstellar travel and time exploration, huge difficulties and constraints temper these fantastical dreams. The inherent unsteadiness of wormholes, combined with the imposing hindrances presented by quantum powers and radiation, causes qualms about their attainability as reasonable methods for transportation. In addition, Einstein's hypothesis of general relativity forces essential imperatives on the speed of development through spacetime, proposing that regardless of whether stable wormholes existed, they probably won't work with faster-than-light travel. A foundation of numerous science fiction stories, notwithstanding these challenges, the charm of wormholes perseveres as a guide of logical interest and investigation. The concept of the S-wormhole, named after its spearheading researcher, typifies the tempting commitment of infinite gateways and substitute real factors, inviting mankind to examine the secrets of the universe and consider the endless potential outcomes that lie beyond. The mission for a bound-united hypothesis that accommodates the apparently disparate spaces of gravity and quantum mechanics has prodded the quest for a theory of everything, a thorough framework capable of integrating all fundamental powers and particles in the universe. At the front of this try stands the famous hypothetical physicist, Michio Kaku, whose momentous work has pushed the investigation of superstring theory. Superstring theory addresses emotional takeoff from ordinary models, conjecturing essential particles are not point-like substances, but rather tiny vibrating strings. These strings, similar to the strings of an instrument, resound at explicit frequencies, bringing about the different particles and powers seen in nature. In this worldview, the universe becomes much the same as a fantastic orchestra, with every molecule corresponding to a novel consonant reverberation of these basic strings. One of the most striking ramifications of superstring theory lies in its potential to make sense of the perplexing peculiarities related to dark openings, wormholes, and other intriguing answers for Einstein's conditions of gravity. As strings cross the texture of spacetime, their dynamic movement prompts the arrangement of gravitational singularities and topological peculiarities. Anyway, the polish of superstring theory veils its innate intricacy, as it requires the presence of extra aspects beyond the natural three spatial aspects and one worldly aspect. These additional aspects, stowed away from direct perception, present a critical test to human instinct. By the way, applied models, for example, the relationship of fish possessing a two-layered lake, give an impression into the tricky idea of these higher-layered domains. The compactification of these additional aspects, similar to the collapsing of a rolled-up piece of paper, renders them intangible at regular scales, yet their impact pervades the very texture of reality. While the exact nature of these secret aspects remains dubious, their theoretical presence offers a promising clarification for the complicated designs and irregularities seen in the universe. Moreover, the numerical underpinnings of superstring theory have started a renaissance in numerical physics, uncovering significant associations between powerful numerical examples and physical peculiarities. Without a doubt, the quest for a theory of everything has catalyzed the association of disciplines, revealing insight into the profound exchange between math and the inherent sciences. In spite of its theoretical class and logical potential, superstring theory remains an untested system, anticipating trial approval. The subtle idea of extra aspects presents an impressive hindrance to trial check, consigning superstring theory to the domain of numerical theory. In any case, the brassy vision of superstring theory continues to spellbind the personalities of specialists and devotees alike, captivating mankind to leave on an excursion of scholarly revelation and exploration. As we venture further into the known spaces of hypothetical material science, directed by the enlightening guide of superstring theory, we defy the tremendous secrets of the universe, balanced on the limit of another period of understanding and edification. The undertaking of disentangling the insider facts of quantum dark openings has long baffled physicists, addressing an amazing test to our comprehension of the major nature of the universe. Notwithstanding various endeavors to handle this conundrum, the tricky arrangement has stayed outside our ability to understand, provoking Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as the 21st century material science that unintentionally fell into the 20th century. Anyway, late headways have infused new hope into the journey for understanding quantum dark openings. A few gatherings of physicists have freely detailed a huge advancement, uncovering that string hypothesis could offer a thorough answer for the issue, yet within the more limited context of two aspects, as opposed to the unlimited 10-layered system set forth by regular superstring theory. While this addresses a promising forward-moving step, the mission for a complete goal remains continuous, with the intricacies of the circumstance presenting significant hindrances. The quest for a bound united hypothesis of everything entices us to test the most profound openings of astronomical presence, where the limits between the real world and hypothesis obscure, and the privileged insights of the universe anticipate disclosure. The investigation of dark openings conveys significant suggestions for how we might interpret the universe, testing our thoughts of reality and bringing up questions about the nature of presence itself. The exchange between dark openings and other galactic peculiarities, like neutron stars and gamma blasts, uncovers the many-sided processes at work in the universe.